I'm going to show you some more examples of polymorphism today. And then after that, we're going to see some techniques for proving new stuff, and we're going to see some new use cases of tactics that we've already seen, as well as some new tactics. Okay. So let's look at this thing here. This is a new type that we defined last time. And basically, it's the product type. It says that if I have two different types, X and Y, I can have just one constructor, which gives me a pair of an element X of type X and an element small y of type big Y. Okay. So I define this type. And then I said that I want to make these parameters here implicit. So I write this, which basically says big X and big Y are implicit arguments in pair. So when I'm writing pair, I only need to give small x and small y. I don't need to give big X and big Y. And then I can easily define some notation. We saw this last time as well. So I'm going to use the parentheses and comma notation to show the pair, and I'm going to show the product type by multiplication. Okay. Now I can write my first function, which used to take a pair of a specific type and give me its first element. But now I can write it in a polymorphic way. So I can say my first function takes two types, X and Y, and it also takes a pair, which is in type X times Y, and it returns some element of type X. And the way it works is exactly as before. So we just match our item P, our pair P, and we say that if it's XY, just return the first element X. Okay, I can define my second function in exactly the same way. So I have implicit parameters X and Y. Remember, we use curly braces for parameters. And then I have a parameter P whose type is X times Y. And I this time have to return a return value of type Y. And again, I match P and I say that if P is XY, just return Y. And of course, I can put an underscore here and also here. So whenever I don't care about something, I can put an underscore. Okay. Now, one more point is that I think I mentioned this in the last session as well. So X and Y are of type. They're types, basically. But you don't need to say this here because Coq is smart enough to figure that out. Okay. So this is a very handy function that we always use. So this is called the zip function or the combine function. And basically it takes two lists, a list of elements of type X and a list of elements of type Y, and it zips them together. It gives you a list of pairs of elements. We saw this in the last session as well. So basically, I'm going to say, let's do a pattern match on both of my lists. And if any of the two lists are empty, I'm just going to return the empty list. Otherwise, if my first list has a head HX and a tail TX, and my second list has a head HY and a tail TY, I just create a new list where I put the two tails together, and at the beginning, I add the pair HX, HY. Okay. So for example, if I want to compute the zip of 1, 2, and 3, 4, I get this. I get a list of pairs, and the first pair is 1, 3. The second pair is 2, 4. So the first element of both lists and the second element of both lists. Now I can also do it when the lists don't have the same lengths. In this case, I will just ignore the extra elements in one of the lists. And you can see this from this definition. So as soon as one of the two lists becomes empty, it's going to return empty. So if I zip true false with 2, 4, 5, this is what I get. My first pair is true 2, and my second pair is false 4, and there is no third pair. Okay, so we covered all of this in the previous session. Let's actually get to new stuff now. So we've already seen what options are, and we've already seen an option on natural numbers. So let's say that now I want to define a polymorphic option. So the whole point of an option was that I can either have a value or my value can just be none. So I have none and some as the constructors of my option. But now this time, when I'm defining this option, it's also taking some x as a parameter. And this x is, of course, a type. Again, I don't need to tell Coq that this is a type. I can be explicit and write it like this, but I don't have to. Coq understands that x is a type. And of course, the inductive definition is also defining a type. And the way we define it is that we say either we have some element small x of type x, or we have none, we have nothing. And just as before, because I don't want to keep writing my type, I'm going to say that big X is going to be an implicit argument for both some and none. I want to write non-nat or non-bool or so on. I just want to be able to write none. And the same thing for some. So I define this. And yeah, this is basically how you define polymorphic options. Now I'm going to end the module here. And the reason for that is that these things are actually already defined in the standard library of Coq. So I'm just going to use the standard ones. So here's a polymorphic version of our famous nth error function. So remember the nth error function said that you give me a list and you also give me some index n, and I will return the nth element of the list. To be more specific, the element at index n, and our indices start with 0. And if it doesn't exist, I have to return none. So if the elements of my list are of type x, then my return value is going to be of type option x. Okay. So, and again, I have this x itself as an implicit argument here. And I say just do a pattern matching on the list. If the list is empty, you should always return none. And again, remember, this is actually non-x. But I don't have to write x because I've made x implicit here. Otherwise, if the list is of this form, it's some element a followed by another list L prime. Then I say, okay, let's do a match on the index n. If the index is 0, I have to just return this very first element a. But I have to be careful about the type. A is of type x, but I need to return something of type option x. So I have to actually return some a. And similarly, if n is the successor of n prime, which means that basically n prime is n minus 1, then I just find the element at index n prime in the tail of my list in L prime. And that's it. This is how nth error works. And again, basically, this is the same as what we had for lists of natural numbers. It's just that now I have this extra type x here as a parameter, and now my nth error is polymorphic. Okay. Now, another really important point that I want to mention is the idea of higher order functions. And some of you have already figured this out in Coq, and it makes sense to you, but I just want to explain it for everyone to make sure we're all on the same page. So a higher order function is basically a function that can take another function as one of its parameters, or a function that can return a function. If I can do these kinds of things, if I can use another function as my parameter or return value, then I say that this is a higher order function. Okay. Now, this might sound very unintuitive, but actually most of the functions we've seen until this point are higher order. And that's how Coq sees them. So here's a very simple example. Let's say that I define a function and I call it simple add, and it takes two parameters. It takes a and natural numbers, and it also returns a natural number. And that natural number is just the sum, a plus b. Now, you might think that this is not a higher order function, because it seems like the parameters that it's taking are just natural numbers, and the return value is a natural number. So there are no higher order function here. But actually it is. So let's define it. And let's do check simple add. And remember, check gives me the type. Let's go back to our higher order function. So I was saying that consider this simple function that takes two parameters and adds them together. And let's check its type. Let's check simple add. And you see that the type is this. The type of this function is nat arrow nat arrow nat. What does this mean? So intuitively, until this point, we were always thinking of this as a function that takes two natural numbers and gives us another natural number. But actually, what this says is that this is a function that takes a natural number and returns a function. And that other function which it returns also takes a natural number and returns a natural number. Okay? So in essence, Coq is thinking of functions with several parameters as being higher order functions. To see this, let's say that I do simple add, but instead of giving it two parameters, I give it one. So first, let's do with two parameters. So if I say check simple add of 2 and 3, it says that the type would be a natural number. But this is basically a natural number which is obtained by taking the function simple add 2 and applying it to the value 3. And now I can see that. I can ask, what is the type of simple add 2? The type of simple add 2 is a function from natural numbers to natural numbers. Okay? Hopefully that makes sense for everyone. So I can actually do definitions like this. I can say I define increment to mean add 1. Okay? So what is the type of increment now? It's a function from natural numbers to natural numbers. And of course, it's a function that does increment. It adds 1. And now I can do compute increment of 5, and it gives me 6. So you see, add 1, this entire expression is basically the same as this increment. It's a function, and I can do increment. But these are not the interesting examples. The more interesting examples are functions that actually take functions as their parameters, even in our intuition, not just from Coq's point of view. So here's a nice function. I'm going to call this apply thrice or 3 times. It has an implicit argument, which is a type x. And it also takes as parameter a function f, which is itself of type x arrow x. So f maps elements of type x to other elements of type x. And it also takes some value n, which is also of type x, and the return type of the apply thrice function is also x. And what it does is basically it applies f 3 times to n. So it returns f of f of f of n. Okay? Great. Now I defined it. So this is very interesting, because now we have combined all of these different things that we can do in Coq. So you see, I have polymorphism here. I have this type x, and of course, I've also made it implicit. And then I'm also taking some function f as the parameter, and I'm also taking n as a parameter, and then I'm applying f 3 times on it. So what is the type of this function, apply thrice? Well, when I'm looking at the type, I actually want to see the type of the explicit version, because I've made this x implicit here. So I put an at the beginning. If I check the type of apply thrice, this is the type. So it says that for any type x, apply thrice does this. It has this type. So it takes a function from x to x and a value in x, and the return type is also x. Okay. And by the way, these parentheses here are really meaningful. It's not associative. You cannot just remove all the parentheses. Okay. So let's see an example of using apply thrice. Let's say I define another function and I call this one decrement, and it takes a natural number, a, and returns a minus 1. Very easy. Now I can say compute applied rise decrement 10. So basically applied rise takes two parameters. The first parameter is another function, decrement. And the second parameter is the number 10. And then it applies that function, which was its first parameter, 3 times to the value which was its second parameter. So it applies decrement 3 times to 10, and it gives you 7. Now, this was polymorphic, remember? So applied rise works with any type X. So I can use the same thing for Booleans. So we had this function neg_b, which basically gave us the negation of a Boolean value. I can say applied rise neg_b false. So it takes false and applies negation 3 times. It will give me a true value. Okay. Now, going on with classical functions, another classical function I'd like to tell you about is filter. So the idea in filter is that, let's say I have a list of elements, and I'm going to be polymorphic. I'm going to say I have a list of elements of type X, and X is an implicit parameter here. So let's say I have this list L of type X, and let's say that I want to just take some of the elements of this list, but I want to take the elements that satisfy a particular test, that satisfy some condition. And the way I actually implement the condition or the test is that the test itself is a function that takes an element of type X and gives me a Boolean, which basically says whether the element passes the test or not. So my filter function has an implicit parameter X, which is the type. It takes another function test as its parameter, and the type of test is X arrow bool. It also takes a list of elements of type X, and of course, it also has to return a list of elements of type X. Okay, how do we do this? Again, we do pattern matching. First of all, I say that if my initial list is empty, just return empty. Otherwise, my initial list looks like this. It has a head element followed by a tail list. Okay, so I have to test the head element. I say if I test the head element and the result is true, if it passes, then what should I do? I should keep the head element and I should filter the rest of the array. So I have to filter the tail, and then I have to put the head element at the beginning. Otherwise, if the head element does not pass my test, I should just apply filter to the rest of the array, to the tail. So I just do filter of test T, and that's it. So if you remember, we have already defined a function called even, which takes some natural number and returns true if it's even. And that function also exists in the standard library. So I can do something like this. I can say compute filter even 1, 2, 4, 5. So again, this is a function, filter. It has an implicit parameter, which is the type. But for explicit parameters, it's taking even, which is itself a function, but it's a function that takes a natural number and returns a bool. And it's also taking a list of natural numbers, and it's filtering it based on this test. So if I do filter even 1, 2, 4, 5, I just get 2, 4. Okay. But now I can do more interesting things. So let's say I have a list of natural numbers. I want to count how many elements in this list are odd. So I can just combine the different functions that I have until this point. So I say first do filter odd L. This gives me all the odd elements, and then just take the length of that. So length filter odd L. That's how I define count odd. And now if I do count odd here, it just counts how many of the numbers in the list were odd, and there are 4 of them. Okay. Another point is that I can also write what we call lambda expressions. Again, I don't know how many of you are familiar with this, but even those of you who haven't done functional programming have probably used lambda expressions in Python or in C++. So these are basically functions that are not given a name. I'm just using the function right here, right now, right? So for example, I can have an expression like this, and this says that this is a function that takes n and returns n times n. Okay, so now I can say compute apply thrice of this function to 2. So basically, I'm going to start from 2 and square it 3 times. Okay, and it's of course 256. Okay. Another thing that is interesting to us is the map function. So let's say I have a function f and I have a list. So I have a list of many elements. I just want to apply this function to every element in this list. So what would it look like? Well, let's say I have a function f and it maps elements of type x to elements of type y. And x and y are implicit parameters here. Of course, I have to have a list of elements of type x. So I should have a list, which is of type list x. And then my return value would be of type list y. Right? And again, I do a pattern matching and it's very easy. I say if it's the empty list, return the empty list. If I have a head followed by a tail, first find the map of that tail. Basically call yourself recursively on that tail and compute f of everything in that tail. And then compute the f of head and put it at the beginning. So it's f of head followed by map of f of tail. Okay. So here's an example. Let's say that my function f is just a simple function that takes x and adds 3 to it. And I say compute map of this over this particular list, 1, 2, 3. So I get 4, 5, 6. Okay. Here's another example. Let's say my function is the even function, which basically tested whether a natural number is even. And I say compute the map of even 1, 2, 3, 4. And as you see, it gives false, true, false, true. And the type is also very important. This is now a list of Booleans. Okay. Now I can have something similar for options as well. So let's say I have a function f that maps from type x to type y. And let's say I have some element of type x, but I don't exactly have an element of type x. I have an option of x. So it's possible that it's none. And I want to apply f. Oops. But I can also return an option y. So basically I say take this value. If the value was none, return none. If it was some x, then apply f to it and return some f of x. Okay. This is also a very common thing that we do when we want to apply functions to an element, but it's already an option. Okay. The next really classical function is fold. Before I give you the definition of fold, I want you to just see this. So the idea here is that I want to say multiply all the elements in this particular list. And the way I do that, I have the mult function, which does multiplication of 2 elements. But I want to say multiply everything in this list and give me the answer. And I also have a starting value, which is 1. So I want to say multiply everything in this list and multiply that by 1 and give me the answer. So that's how fold works. So based on this example, let's come back and actually see the definition of fold. So it takes 2 implicit type parameters, x and y. And this is the function that it takes as a parameter. It takes a function f of this type. We'll come back to this. But the idea is that I have a list and every element in this list is of type x. And I want to kind of fold this list into just one element of type y. So I want to just return one element of type Y. Okay. And the way my folding works is that I know what the default value is. The default value is B, and that's the value that I'm going to assign to the empty list. And then if I know the value of some list, and if I also, if I know that folding something leads to some value in Y, and if I also know the value of the head, I can fold everything together and get another element in Y. So the definition actually probably makes it even easier to understand. So if I have the empty list, I'm just going to return the default value B. If I have a list that looks like this, head followed by tail, I'm going to first fold the tail recursively, and then I'm going to say fold the head in. But the way that I fold the head in is that I apply this function f. So I say f of h and fold of the tail recursively. Okay. And again, if you look at this, so for example, if I ask what is the type of fold and b was the Boolean and. So this is a function, the entire thing, fold and b is a function that takes a list of Booleans and a particular Boolean and returns a Boolean. And if I check the type of fold mult, it takes a list of natural numbers and a natural number and returns a natural number. So here's an example again. So let's say I want to do fold of mult. Mult was multiplication, 3, 5, 2, and 1. Okay. So what am I doing here? I'm saying my function f is multiplication. Okay, so think of f as multiplication here. So I'm saying if you have the empty list, return 1. If you have a head followed by a tail, first find the multiplication of all the elements in the tail, and then multiply that result by the head. Okay. So in this case, I'll just get the multiplication of everything in this list. So I get 30, which is 3 times 5 times 2. And I could change the initial value. I could, let's say, put 2 as the initial value, and I would get 60. Okay. Let's just do a few more examples of these things. Here's another thing that we use very often. Let's say I want to define a constant function. Okay. So this function const fun, it takes an implicit type x, and it also takes a particular value of this type, and it returns a function. And the function that it returns is the constant function from natural numbers to x. It's the constant function that always returns small x. Okay. So I define it like this. And again, this is a lambda expression. So it's a function that takes any natural number k and just ignores k and returns x. So for example, I can say, take the constant function that always returns false. Okay. And I call that f false. And then I can say compute f false of 1. This is false. It's the constant function. I can say compute f false of 60. It's false. I can check the type. And as you see, the type is a function from natural numbers to Booleans. So const fun returns a function. It's a function that returns another function. And finally, the same thing that I said about this very first example, simple add, it also works for the addition in the standard library, which was called plus. So again, if I check the type of plus, actually plus and add are the same thing. So the type is this. It's a function that takes a natural number and returns a function that takes a natural number and returns a function. Okay. So this is the domain. This is the codomain. And again, I can define a new function, I can call it plus 10, and I can just define it as this, plus of 10. So this is a function that just adds 10 to whatever you give it. And then I can compute plus 10 of 5, and that's 50. Let me also give you something to prove later. So let's take this fold, and let's say that I have a list of natural numbers, and I want to add all the elements. I want you to prove that we will get the same result if we add all the elements in a list of natural numbers or in its reversed list. So I'm going to call this rev add fold. So I'm going to say for any list L of natural numbers, I have this fold mult L, fold add L0 is equal to fold add reverse of L0. I'm going to write admitted, but I want you to prove this. Not right now, but after the class. So let's actually go to the next topic, which is more proof tactics. So proof tactics are these small things that we write in our proofs, basically. We've seen a lot of them already. We've seen intros, we've seen rewrite, reflexivity, assumption. But let's start with a very trivial theorem. So I'm literally calling it trivial because it is. And this is my theorem. I'm saying that for all natural numbers n and m, if n is equal to m, then n is equal to m. So it's the same thing on both sides. Now, how would we normally prove this? Well, we would first say do intros so that n and m are added to this context here. And then our goal is to prove that n is equal to m. So let's do a rewrite using h. And then we have m equals to m. We have the same thing on both sides. We use reflexivity, and that's it. Now, instead of this rewrite, we could actually say apply h. So take the same theorem again. I do intros. And here I just see that, well, h has what I'm looking for. It's a hypothesis. So I just say apply this hypothesis h. And I apply h. And again, it's just an easier way in comparison with writing rewrite and reflexivity. I can just write apply. But actually, apply is more powerful than this. So here's another theorem. This is actually kind of longer. So let's say that I have 4 natural numbers, n, m, o, p, and I want to prove this. I want to say if n is equal to m, and if n equal to m implies that no is equal to mp, then no is equal to mp. Okay? And these are lists, of course. Now, this is again very simple. I'm going to start a proof. I'm going to do intros. And now here's the thing. I want to say that no is equal to mp. But I have this on the right-hand side of h0. So I have my goal on the right-hand side of h0. So I can just write apply h0. And if I do this, it will tell me, okay, now you have to prove the left-hand side of h0. Right? So the goal changes. You see, the goal was this. It was the right-hand side of h0. And I say apply h0. And it says, okay, now prove the left-hand side. Now, of course, the left-hand side in this case is just h. So I can say apply h. And that's it. Okay. Here's another kind of trivial theorem. It is longer, so I'm going to give you some time to just write it. What does this say? It says that if nn as a pair is equal to mm, and if I know that for all q and r that are natural numbers, qq equal to rr implies that the list that only contains q is equal to the list that only contains r, then the list that only contains n is equal to the list that only contains n. Be very careful with the parentheses when you're writing this. Okay, so let's do our proof. And again, we have for all, so we do intros, we bring everything in context. This is what I want to prove. I want to prove that this list, it's a list with one element, is equal to this list. Okay, but how can I do this? Well, I don't have this on the right-hand side of any of my assumptions, but this particular assumption, EQ2, it's actually quantified. It has universal quantification. So it says for every natural number Q and R, this holds. So specifically, it also holds for Q equal to N and R equal to N. Right? So apply can also understand these kinds of things. So here I can just say apply equation 2. And it just understands that it has to do a matching, and it has to match N to Q and M to R. And so if I do this, it will give me this left-hand side. So you see, I do apply EQ2. So Q was N and R was M. So now I have to prove that NN is equal to MN. So apply is actually quite smart. But now this one is just my equation 1, so I can say apply EQ1. Or as we've seen before, I can also say this is an assumption. Here's the theorem I want you to prove. So I want you to prove that for all P, if for all N, N being even means that the successor of N is not even. And if for all N, N being even, N not being even means that the successor of N is odd. And if P is even, then the next of P, the successor of P is odd. Our common sense says, let's do intros. And now this is what I want to prove. I want to say that odd of the successor of P is true. Okay. So where do I have something that can match this kind of pattern? I have it here, right? So H0 says that for every natural number N, if this condition is satisfied, then odd of N is true. So just looking at it syntactically, I can see that I should probably apply H0. Okay. So I apply H0. And now I have to prove this one. I have to prove that even of S of P is false. But now again, the question is, where do I have something that matches this on the right-hand side of an assumption? And I have it in H. Okay. So here I have even of S of N is false, and this is quantified. It's for all N. So I can just substitute P for N, and I can apply H. So I apply H. And it says, well, now you have to prove that even of P is true, and that's H1. So I can just apply H1. Now, one thing I want you to really notice in this proof is that when I was figuring out what to do, I wasn't doing any kind of smart or semantic reasoning here. I was just saying what matches syntactically. What can I apply? Let's just try to apply whatever I can. And for this particular theorem, that was enough. But of course, normally I would expect you to really reason about how I want to get to these things, right? So when I do this intros, here's the thing. My first assumption is saying that for every N that is a natural number, if N is even, then the next number, N plus 1, is not even. The second assumption says that if N is even, if N is not even, then it's odd. Okay. And I'm saying that P is even. And I want you to say that next of P is odd. Okay. So how would you normally do this? Normally you would do forward reasoning, right? You would think that, okay, what do I know? I know that P is even. So I can apply this one, and I can say that P plus 1 or S of P is not even. And then I can apply this one, and I can say if it's not even, then it's odd, right? So we're doing forward reasoning when we're reasoning like as humans. But actually here in Coq, we're doing backward reasoning. So it's the same argument, but we're doing it in the opposite direction, right? So I'm saying I want to prove this. How do I prove this? I take the same argument, but in the opposite direction. I say, first, let's apply H0. It's like when you're reducing a problem to another problem. Let's first apply H0 so that I just have to prove this one. And I apply H0. Now I say, let's apply H so that instead of this thing on the right-hand side, which I have to prove, I have to only prove the left-hand side, of course, after substitutions. And then I apply H1. So you see, intuitively, I would say, if I was doing reasoning as a human, I would first apply H1, then H, then H0. But here, it's the opposite direction. Okay. So prove this one. This is another trivial thing. I have two natural numbers n and m. I want to say for all n and m, if n is equal to m, then m is also equal to m. You should be able to solve this using, let's say, rewrite. By the way, remember that we're doing all of this so that we can have formal reasoning of programs at the end. So I'm just teaching you a lot of Coq, and at some point our theorems will really change, and instead of proving theorems about natural numbers, we will be proving theorems about programs. Okay, let's do this. So first I do intros, and then we've seen this before. I can do rewrite using H because I have H here. And it says n is equal to m. So if I do rewrite using H, I just get m equals. And I can do this rewrite in any direction. I can do in this direction, or I can do in this direction, and both of them work. Because both of them give me the same thing on both sides, and then I can say reflexivity. But now I want to show you how we can do this with apply. So let's say I do intros. Can I just say apply H? So my hypothesis is that n is equal to m, and I want to prove the same thing, except that I've changed, I've swapped the left and right hand side. No, if I say apply H, it says, well, they don't really match. I cannot apply H. But here's what's interesting. We have another tactic called symmetry. And you can use symmetry. And basically what symmetry does is that when you have an equality, it swaps the two sides in the goal. So I do symmetry. Look at my goal here. So before doing symmetry, this is the goal, m equals to n. I do symmetry, and now the goal is n equals n. And now I can just apply H. Okay. And then, well, I don't need these things. Okay. Here's another theorem that I want you to prove later, but let's just see what the theorem is. I want to first use it, and then we'll come back to prove it. So I want to say that for any type X and for any list of elements of type X, if I take this list L and I reverse it twice, I will get the original list. Okay. For now, I'm just going to say this is admitted. Again, we will come back and actually prove this, or I will give it to you as a homework. But I want to use it right now because our focus is on how to use apply. So let's say that I want to prove this other theorem, and I want to use this theorem. And the other theorem is this. I want to say for any two lists that are lists of natural numbers, if L is the reverse of L prime, then L prime is also the reverse of L. So prove this, and you can use the previous theorem. I want to prove that L prime is the reverse of L, and my assumption is that L is the reverse of L prime. So I can first do a rewrite using my assumption so that I get this. I get that L prime is the reverse of L prime, because I'm replacing L with reverse of L prime. Okay. Now, I want to just apply this previous theorem, rev twice, because it seems it's the same thing. So I just say apply rev twice. But this doesn't work again. And again, we have the same problem. The problem is that here I have the two reverses on the left-hand side and the list on the right-hand side, but here the list is on the left and the two reverses are on the right. So I actually need to first apply symmetry. I do symmetry, and now it says prove this, and now I can say apply the previous theorem, apply rev twice. And this is okay. Try this one. So this one says that if the list AB is equal to CD and CD is equal to EF, then AB is equal to EF. Okay, so let's do intros first. And then let's just try rewriting, right? So AB is equal to EF. In H, I know that AB is equal to CD. So let's do a rewrite using H, and I get CD equals EF. And now I can just say assumption, or I can say apply H0, or I can actually do it with rewrite. I can say rewrite H0 and then reflexivity. But I don't like this proof. I would actually prefer it if I can write a more general case and then just apply that general case here. So what do I have here? I'm saying that if some list is equal to a second list, and that second list is equal to a third list, then the first list is also equal to the third list, right? So I'm saying that equality is transitive. But this doesn't only hold for lists, it holds for everything. So let's just prove a general theorem that says that equality is transitive. And after proving that, we can come back and then apply it on this particular example. So try to prove this theorem. It says that equality is transitive. So it says for any type X and any three elements N, M, and O of type X, if N is equal to M and M is equal to O, then N is equal to. Actually, to be more specific, I'm not using AND here. I'm just using implication, but it's the same theorem. We have universal quantification, so we do intros, and I want to give some names to the equations that I get in my intros, so I do it like this. And then I can just do rewrites, right? So I want to do a rewrite. This is basically the same proof that I gave here. It's just that rewrite using equation 1. So N is equal to O. I'm doing rewrite using equation 1. So I put M instead of N. And then this is already equation 2. And so I can do rewrite using equation 2 and reflexivity. Or I can just say this is an assumption. Okay. So now we can go back and look at our example again. So this was our example. We said that for any 6 natural numbers A to F, if AB is equal to CD and CD is equal to EF, then AB is equal to EF. Okay. So in my proof, this time I first do intros, again, just to get rid of the quantification. And now I say this is a special case of this general theorem that I proved here. I proved that basically if something is equal to some other thing, and that second thing is equal to a third thing, then the first thing is equal to the third thing. It's just that my things here are actually lists of natural numbers. So if I want to do this, can I just say apply trans EQ, apply what I have here. And as you see, this one fails. Now, why does it fail? So let's say that I want to apply this theorem. So Koch tries to, again, do a matching of the variables and figure out what has to replace what. So in this case, we want to prove that AB is equal to EF. So Koch understands that instead of N, it should plug in AB. And instead of O, it should plug in EF. Okay, so Koch understands those things. And because N and O have type NAT list, Koch also understands the type of X, understands that X is also NAT list. Right? So Koch can figure out what X is, what N is, and what O is when it wants to apply trans EQ. But it cannot figure out what it has to plug in for M. That's not something that it can just understand based on the goal. So I have to explicitly say what to plug in for M. So I can't just say apply trans EQ. I have to say apply trans EQ, and I have to say what to replace M with. And in this case, I want to use the list CD as my value for M. So I say apply trans EQ with M equals to CD. Okay. And I do this. Great. Now it says you have to prove two things. You have to prove AB is equal to CD, but that's an assumption. That's equation 1. So I just say apply equation 1. And then it says you have to prove CD is equal to EF. I apply equation 2. That's it. So you see, we can have this kind of thing. We can have an apply, and then we can say apply it with, and then we can say what parameters should be replaced by. Okay. Here's another example. Let's say that I define a function called -2. And this is just a function that takes n and returns n minus 2. Okay. Now I want you to prove this. So I want you to prove that if m is the -2 of O, so if m is O minus 2 basically, and n plus p is equal to m, then n plus p is also -2 of O. Now, the point of this example is to make sure you don't really use -2 at all. So again, we have three things that are supposed to be equal. Right, so I know that m is -2 of O, and m is also n plus p. And I want to deduce that n plus p is equal to -2 of O. I expect you to apply the transitivity of equality, trans EQ. So here's how we can do this. We start our proof. We, of course, do intros. And then now I have to apply trans EQ. But again, as before, if I just write apply trans EQ, it says I don't know what to put for M. So in trans EQ, it can figure out what to put for O and N. So for O, it has to basically put -2 of O, and for N, it has to put N plus P. But it says, what should I put for M? And actually for M, it should put M, but these are two different M's, right? So I have an M here, which is basically the variable in my context. And then I have an M here, which is a variable in trans EQ. These are not the same. So what I have to say actually is something that looks really weird. I have to say apply trans EQ with M equal to M. And what this means is that this is the M in trans EQ, this is the M in my context here. It says put this M for that M, and then it works. Yeah, it works. And then now I say, I want to show that N plus P is equal to M, that's H0. I want to show that M is -2 of O, that's just H, and that's it, QT. Okay. we have one theorem that we didn't really prove because we were focused on saying how to do apply, and now you know how to do apply and how to do apply with. But let's go back here and prove this theorem. So prove this ref twice. So it says for any list of elements of type X, if I take the list and I reverse it twice, I will get the same list. Do you want to already do induction here? Can we do simplify or anything else? No, it doesn't do anything, right? So let's do induction. Induction on what? On L, of course, because L is the only thing that is inductive here. And let's say I'm going to call it L prime, or, well, I'm going to have this situation because remember that my list was either the empty list or it had a head and a tail. So I'm going to say use H and T as the head and a tail. Okay, the base case is to just say that the reverse of the empty set is the empty set. Okay, I can easily say reflexivity and it already solves it. Or I can just say compute both sides first. Both sides are the same, so reflexivity. Okay. Now I have this. My induction hypothesis is that if I take my tail, the reverse of the tail is the tail itself. Okay, but now I want to say that instead of just having a tail, I have a head followed by a tail. And I want to say that the reverse of the head followed by the tail is the head followed by the tail. Okay, what can I do here? Let's do simplify and let's see what we get. So this is what we get. This reverse inside simplifies. It says it's the reverse of the tail appended with H. What should I do now? So I now need a lemma that tells me how I can get rid of this append when I have a reverse, right? So this is the kind of thing that I have. I want to have a lemma that basically says for all X that is any type, and for all, yeah, actually, let's write it like this. For every X that is a type, and for every H of type X, and for every T of type list X, if I take reverse of T and add H, and if I reverse that, that's going to be H followed by, well, I don't need it to say reverse, okay. If I have this, the reverse would be H followed by the reverse of T, right? So this lemma, let's say admitted for now. Let's come back here. So I want to apply this lemma. So I say apply LM1. Doesn't work. What should I say? How can I apply this lemma here? Yes. So I first do an assert. Let's call the assertion A. What is the assertion? I want to say reverse of T followed by H is equal to H followed by reverse of T, right? Okay, I assert this. And now I can say apply lemma 1, and it knows how to apply it. Great. Now I have this A, so I can say do a rewrite using A. Okay, so now what do I have? I have H followed by the reverse of T is the same as H followed by T. But my induction hypothesis already says that reverse of T and T are the same. So I can do a rewrite using my induction hypothesis. And now I have the same thing on both sides. So I can say reflexivity. But now I have this lemma to prove. And unfortunately, we ran out of time. So you should be able to prove this lemma, though. This is not a hard lemma. I'm going to start with recalling some of the things that we have already seen. And I'm creating a module here because I'm defining things that already exist in the HKUST standard library, and I don't want to create any conflicts here. So let's say I just create a new module. So remember how we define natural numbers. So we said a natural number is a type that is defined inductively, and it's either O, which was a constructor that basically showed 0, or it's the successor of another natural number. Okay. Now, the thing that is very important to understand here is that whenever you define something inductively, these constructors that you have, O and S and so on, they are first of all disjoint. So O is not really the same as any one of the values that you can get with S. So I have no case where S of something is equal to O. Okay, and that's by definition. This is already inside this definition. And the other point is that each one of these constructors are actually injective or one-to-one on their own. So if I have two numbers that are different, so if I have A and B and they're not the same, then S of A and S of B are also not going to be the same. Or another way of looking at this is that if S of A is equal to S of B, then A is equal to B. And this is also by definition. So whenever I'm defining an inductive type and giving it several different constructors, I'm assuming that every constructor is one-to-one, injective. And also I'm assuming that the values that are taken by, that are created by different constructors are never the same. Okay. The other thing that I want to recall is this definition of predecessor, which basically said that if I have a natural number n, and if I want its predecessor, I can find it like this. I can say, do a pattern matching on n, and the predecessor of O is O, or predecessor of 0 is 0. And if n is the successor of m, then m is the predecessor of n. Okay? So this is all I wanted to recall for you. But let's actually give a proof. So let's say I just said that this S is an injective function. This S is a constructor here. But if I check the type of S, so if I say check S, you see that it's a function basically that takes a natural number and gives me a natural number. Of course, the natural number that it gives me is the next natural number. So I want to prove that this function S or constructor S is injective. So prove this theorem. S is injective, which means that for every n and m that are natural numbers, if S of n is equal to S of m, then n is equal to m. Okay, so let's see this. So first I do intros because I don't want to have for all in my goal. And here's the thing. My assumption is that S of n is equal to S of m. And I want to prove that n is equal to m. So I just use an assertion, and this is the assertion that I use. I say that n is the predecessor of its own successor. Okay? So I want to prove this. I can just prove this by reflexivity, because if I simplify it, both sides simplify to n. And so I can do this. I can say simplify, and you see both sides are n, and then do reflexivity, or I can just directly say reflexivity. Now that I have this extra assumption here, I know that n is the predecessor of its own successor. I can do a rewrite, right? I can rewrite using H2. So I want to say that n is equal to m. I do rewrite using H2, and I get that predecessor of successor of n is equal to m. But I know that the successor of n was the successor of m. That was my very first assumption. So I rewrite using that assumption, and I replace this successor of n with successor of m. So now I have that predecessor of successor of M is equal to M, but if I simplify it, both sides will simplify to M. And then I have reflexivity. Okay. So this proves that, of course, S is injective. But the really important point, and the point that I said at the beginning of this session, is that all constructors are injective, and the values created by different constructors are destroyed. Okay. So to prove the injectivity of all constructors, I can actually extend the same idea of proof to all of them. So the same kind of assertion. What's the role of the predecessor function here? Basically, the role of predecessor is that it undoes whatever S did. It removes one S, right? So if I have any other type, let's say I have this type, I'm just calling it my type, and it has two constructors. The first constructor takes only one natural number, and the second one takes two natural numbers, okay? Here's what I want you to do. I want you to prove that the first constructor is injective. So that means that for all A and A prime that are natural numbers, cons1 of A equals cons1 of A prime implies that A itself is equal to A prime. You should be able to basically use something very similar to the previous proof. So what do I need? In order to give a proof like this, I need something that looks like the pred function. I need to write some equivalent function to what predecessor did in the previous proof. I have to write a function that basically removes cons1. It's like an undo function. Okay. So here's what I do. I call it cons1 unroll, or you can call it whatever you like. It takes some value x of my type and it returns a natural number. And it does it with a pattern matching. But remember, I had two constructors. So when I do a pattern matching, I have to actually make sure I have cases for both of these constructors. Now, honestly, I don't care about the second one. I only care about what I do with the first one. So I say if it was cons1 of A, return A. If it's cons2 of AB, I can return whatever. I don't really care. I'm returning A here, but let's say I return 100. Who cares? Okay. The important point here is that if X is created with the first constructor, if X is cons1 of A, this function returns A. I don't care about the other case. Now I can use this to prove my theorem, which says that the constructor cons1 is injective. Okay. So again, our assumption is that cons1 of A is equal to cons1 of A prime. And we want to prove as the goal that A is equal to A prime. Of course, we will have this only after we do intros. So let's do intros. Okay. Now I'm going to assert something that is basically the same as what I asserted with pred and successor, like pred and S. I'm going to assert that A is equal to the undoing the cons1 unroll of cons1 of A. Okay. I assert this. And again, this is just following the definition. I can do simplify, or I can do compute, and it just computes both sides as A. And then I can say reflexivity. So now that I asserted this, I have it in my assumptions, and I can use it as an assumption. I have H2. Okay. So now I rewrite my goal using H2. So it means that I replace this A with this entire thing. Okay, rewrite using H2. But now I have cons1 of A here. And my first hypothesis here says that cons1 of A is equal to cons1 of A prime. So instead of this, I can put cons1 of A prime. So I rewrite using H1, and you see it becomes cons1 of A prime. And now, again, both sides are just A prime. If I simplify or compute, I will get A prime on both sides, and then I can say reflexivity. I can also directly say reflexivity, but I want to show you that simplify actually gives A prime equals to A prime, and then I do reflexivity. Nice. Now I want you to prove the same property, the injective property, for cons2. for the second constructor. The difference here is that const2 actually took two parameters, a and b, which were natural numbers. So of course you can do this with any number of parameters, but I just want you to do an example with two parameters so that you see how this works. So prove this theorem. The theorem says that if I have AB, A prime, and B prime, and const2 of AB is equal to const2 of A prime, B prime, then A is equal to A prime and B is equal to B prime. Again, you should try to apply the same idea. So try to write a function that undoes const2. Okay, so in this case, I'm actually going to do two different functions. I'm going to use two functions because const2 had two parameters. So I'm going to have one function that returns the first parameter and one function that returns the second one. So I'm going to define it like this. I'm going to say I have const2 unroll A, which basically takes X and it matches it. And if it's const1, again, I don't care what it returns. Let's say it returns something. And if it's const2 of A and anything, again, I don't care about B, it just returns A. And then I have a different function, which is again the same thing. So I don't care about const1. Yeah, here I don't care about const1, and here I don't care about A. If it's const2 of anything and B, I just return B. Okay, now this is my theorem. I want to show that const2 is injective. Again, I first do intros. So my assumptions are that const2 of AB is equal to const2 of A prime, B prime. And that all of these variables are natural numbers. So first of all, I have a conjunction here. So we've seen this in the very first session on Coq. We can actually use split, right? And if I do split, I'm basically saying that I will prove the first part first, and then I'll go to the second part. So I do split. Okay. Now I want to prove that A is equal to A prime. Now I use the same assertion as before. I say if I take A, if I take const2 of AB and I do the unroll A function on it, I will get A. So I assert this, and this is true because I can simplify and just follow the definition. So I can just write reflexivity. Now I have it as an assumption. Now I want to prove that A is equal to A prime, but I know that A is const2 unroll A of const2 of AB. So this is H0. So I use H0 to replace this A with this entire expression. So I say rewrite using H0. Now I have this. But I know that const2 of AB was equal to const2 of A prime, B prime. That was my very first assumption. So I just do a replacement where I replace this part. And this is rewrite H. And finally, if I now simplify both sides, I'll get A prime on both sides, and then I can say reflexivity. Now I have to do the exact same thing for B, except that I'm going to use the second unroll function. So I'm going to assert that B is equal to const2 unroll B of const2 of AB. Okay. Again, the proof is simple. I simplify and I use reflexivity. Now I have this assumption. I know that B is equal to this thing, so I can replace B with that thing using rewrite. And now I have const2 of AB. I know that it's equal to const2 of A prime, B prime. I can use a rewrite using H. And finally, I just simplify. I get B prime on both sides, and it's reflexivity. Okay. Now, as you saw, these proofs were kind of hard. And of course, it gets even harder if you have more parameters. If I have 10 parameters, I have to write 10 of these functions and 10 assertions and all of these proofs. And actually, Coq has a tactic which is called injection. And you can just use that. So here's a simpler proof of the very first theorem that we proved this in this session, which is like M are natural numbers and successor of N is equal to successor of M. Then N itself is equal to N. So we start our proof, we do intros as usual, and then here's the new tactic. I say injection H as H0. So I'm saying take H, H is one of my assumptions. and I'm saying apply injection on this. And basically what that means is that if S of n is equal to S of m, I can instead say that n is equal to m. So I can just write actually injection H without adds or anything. If I just write injection H, you see that it found that n is equal to m, and then it added it at the beginning of my goal. So instead of proving my goal, now I have to prove this simpler version. But if I write injection H as H0, let's say, then it just changes the name. So H becomes H0, and also it removes the S. So, and now I can say apply H0, and I don't have any. Okay. Solve this one now. So let's say that n, m, and o are natural numbers, and the list nm is equal to the list oo. Prove that n is equal to m. And of course, I want you to give a proof using injection. Don't just redo the entire proof. Like, use injection. Here's our proof. As usual, we do intros. We're doing intros at the beginning of every proof at this point. Okay, so here's the thing. H is actually a list. And we saw the definition of list in the previous sessions. So if I say something like this, if I say set printing all, oops, set print all. How did I write this? Okay, yeah. Set printing all. If I write this, it expands everything and doesn't use any of the notation and syntactic sugar. So H says that this list is equal to this list. But if I do set printing all, it actually writes the entirety of these lists. And you see the constructors of the lists and so on. So you have const nat n, const nat m. This is the list nm, and then followed by nil. And the other list is const nat o, and then nil, right? So I can use injection here, and I'm actually using the injection of cons. And if I use injection of cons, that basically tells me that, well, if the first one is equal to the second one, then this sequence should be equal to that one, and so on. So I should get something like this. So I do injection on H. And actually, let me do it like this. I say injection on H as H0. So you see, I had that nm should be equal to oo, but when I do this, I get that n should be equal to o and m should be equal to o. So injection is also applied exhaustively. It just applies injection as many times as it can, and it finds all the possible equalities that you can get by injection. So let's say I just do injection H so that I add this here to the left-hand side of an implication in the goal. And then I do intros so that they come up here. Okay. Now, what do I know? I know that m is equal to o, n is equal to o. I want to say n is equal to n. I can just rewrite using H0, and then I can apply H1. Or actually, I could also use one of the theorems that I proved before, that equality is transitive. Okay. So prove this one now. So this is another example of how you can use injectivity. We want to say for any type X and any three elements A, B, C that are of type X, and any two lists, L and J, which are lists of type X, I want to say that if ABL is equal to CJ and J itself is equal to CL, then A is equal to B. Okay? So intuitively, what am I saying? A, B, and C are elements here, but L and J are lists. So I'm saying that ABL is equal to CJ, but J itself is CL. So ABL is equal to CCL. Right? And from the fact that ABL is equal to CCL, I want to get that A is equal to B. So here you have to actually rely on the injectivity of the constructors for a list again. So let's do the proof. So I just assert the thing that I said is my intuition here. So as a human, when you look at this, you say that, okay, ABL is equal to CJ, but J itself is CL. So ABL should be CCJ, right? Or sorry, yeah, ABL should be CCL, right? So, okay, let's do this again. As a human, you look at this and you see that ABL is equal to CJ, but J itself is CL. So ABL is equal to CCL. That's what I want to assert. I want to assert, and I give it the name big A, that ABL is equal to CCL. Okay. Now, how can I prove this? Well, I have this assumption H here, which says that ABL is equal to CJ. And remember that A and C are both basically letters. They're one element, whereas L is a list. So ABL is the list that is obtained by taking BL and adding A at the beginning. CJ is the list that is obtained by taking J and adding C at the beginning. So both of them are created with the same constructor, cons. So if I apply injection on H, you see that I get several things here. First, I get that BL is equal to J, but more importantly, I also get that A is equal to C. And now again, I do intros to bring this into the context instead of the goal. Okay. So now I have to prove that ABL is equal to CCL, but I also know that A is equal to C. Okay. So I'm going to do a rewrite using H1. What does H1 say? It says that BL is basically the same as J. So instead of this BL here, I can put J. So I get AJ is equal to CCL. But now I know that A is the same as C. So I can do another rewrite using H2 and replace this A with a C. So now I have that CJ is equal to CCL. That's what I have to prove. Okay. But what does H0 tell me? H0 tells me that J is CL. So I can replace this CL here with J. So I do rewrite H0, and now I have the same thing on both sides. I have CCL equals CCL. So I do reflexivity. And all of this was to just prove my assertion. Okay. So now I have my assertion in my context, and I can use it here as an assumption. So I know that ABL is equal to CCL. And I want to prove that A is equal to B. Right? How do I prove this? How do I prove that A is equal to B? Well, again, I can take this, and I can look at their constructors. So I don't care about the tail. This is a list that is obtained by adding A at the beginning of some other tail. This is a list that is obtained by adding C at the beginning of some other tail. So if I apply injection, I will get A equal to C. Of course, I will also get that this tail is equal to this tail, which means that BL is equal to CL. Okay, so I do injection. And actually, injection is exhaustive again, so it applies it again. So BL is equal to CL means that B is equal to C and L is equal to L, but L equal to L is trivial, so it doesn't add that one. It just adds that B is equal to C and A is equal to C. And now I do intros to bring this into my assumptions. And again, at this point, I know that A and B are both equal to C, and I just want to show that they're equal. So we are back to transitivity of equality, but I can also do it with a rewrite. So I rewrite it, and then I say this is the assumption, or I apply the other one, and that's security. Okay. So this was a bunch of theorems that we could actually prove using injectivity. But the other point that I said was that if I have two different constructors, the values that are created by different constructors are always going to be disjoint. So I will never have the same value created by two different constructors. Okay. I can actually use that when I want to prove something. So, for example, let's say that I want to say for every n and m that are natural numbers, if false is equal to true, then n is equal to n. Okay. So logically speaking, this holds vacuously because like the left-hand side of the implication never holds. So the entire implication is always true. But here's the thing. What are true and false? It goes back to the definition of the type Boolean. Remember when I defined the type Boolean, I said that we have two different constructors, true and false, and none of them really took any parameters. So here's my proof. Of course, I'm doing intros first. And now I'm saying, look at H. H says that false is equal to true. These are two different constructors. They cannot be equal to each other. Now, how can I tell Coq about this? Well, I can use the tactic discriminate. So I can tell Coq that, well, do discriminate on H, which means that the left-hand side of H is created using a different constructor than the right-hand side. And that means that H is a contradiction, which means that, well, my goal is proven, because if you have a contradiction in your assumptions, you can get anything from a contradiction. So I say discriminate H, and it suddenly says no more goals. Now, instead of saying discriminate H, I could also just say discriminate, and it will just try to apply discriminate to all of the assumptions in the context. And even if one of them works, it says, okay, you're fine. So I don't have to necessarily specify where I want to do the discrimination. You already saw the proof for this one, but anyway, prove this one. So I want you to prove that for all natural numbers n, if the successor of n is 0, then 2 plus 2 is equal to 5. Right? So that's again because the successor of n cannot be 0. Okay, so let's see the proof. Yes. So we do intros, and again, I can immediately say discriminate H here. Because remember the definition of the type nat when I was defining natural numbers. 0 is just a nice way of writing O. So I had two different constructors. I had O and I had S. So on the one hand, I have S, and of course it has some parameters. And on the other hand, I just have O. So S of something can never be equal to O because the constructors have to be disjoint. So I can just say discriminate H, and that's it. Here's another one which is very similar, but this one is actually a little bit harder to understand, but the proof is basically the same. So it says that for all types X and for all elements X, Y, Z of type X, and all lists L and J that are lists of X, if X, Y, L is equal to the empty list, then X is equal to Z. So again, here what we have is that on the left-hand side, I'm sure that this list is not empty because at the very least, it has X and Y. Right, so it has at least two elements. So again, intuitively, this makes a lot of sense because if my left-hand side is a contradiction, I don't care what my right-hand side is going to be. So I'm going to do intros again. And now here's the thing. This H, on its left-hand side, it has X0, Y0, L. On its right-hand side, it has the empty list. Now, if I again write set printing all, the left-hand side is actually this one. It's like cons of X0 and Y0 and so on. Whereas the right-hand side is just nil. And remember, cons and nil were two different constructors for the type list. So the fact that the two sides are using different constructors means that they cannot be equal. So I can easily say discriminate H, and it sees constructor on this side is const, the constructor on this side is nil. And that's it, no more goals. Great. Now prove this one. So remember the difference between equals and equals question mark. The difference was in the type. So if you use equals, you get a proposition. If you use equals question mark, you get a Boolean. Okay, now I want you to prove this. I want you to prove that for all n, if 0 equals n as a Boolean, this thing is equal to true, then n is equal to 0. And you can also check what equals question mark does. So it says it's a function that takes two natural numbers and returns a Boolean, and this is how it works. So it takes two natural numbers n and m, and it does a pattern matching on n. It says that if n is 0, and then do a pattern matching on m. If m is also 0, return true. Otherwise, if m is the successor of something, return false. The other case is that n itself is the successor of n prime. Then again, it says that if m is 0, return false. If m is the successor of m prime, call the same function on n prime, m prime. So equals question mark is just syntactic sugar or notation for EQB. Okay, let's actually see the proof. So we do intros first. Now, here's the thing. I have this natural number n, and basically I want to do a casework on n, right? Because here I'm checking whether n is 0 or not. So let's do a casework. And we do casework by destruct, of course. So I say destruct n, and I call the parameter to s as n prime, and I keep the equation. So I destruct it, I get two cases. The first case is when n is 0, and the second case is when n is not 0. So the first case, if n is 0, I can, well, let's do an intros first. And you see that I have to just prove that 0 is equal to 0. And this is easy. This is reflexivity. Okay. Now, the second case is that n is not 0, which means that n is the successor of some other number. Let's say n is the successor of n prime. And so here also, instead of n, I now have successor of n prime. Okay. So now if I do simplify, what would happen? So if I do simplify, all of this will simplify to false. Why will it simplify to false? Because this one, it's basically O, remember? And this one was S of n prime. And then in the definition of equals question mark, we had that if the first number is O and the second number is S of something, it's false. So if I simplify here, I get false. And of course, this true remains true. So now this is what I have to prove. I have to prove that if false is equal to true, then S of n prime is 0. But now I can do intros. I get false equals to true up here. And now I can say discriminate on H, because false is never the same as true. False and true are two different constructors for bool. And that's QED. Now, but a very weird thing that I did here, and this is the first time that I'm doing something like this, is that I didn't do intros first, right? So up until this point, whenever we've had any kind of entailment like this, we would just do intros. Okay, so here, if I first do intros, what happens? This thing goes up here into the context. But then my problem is that I cannot simplify it anymore, because simplifies the goal, right? So I don't want to do intros first. I want to first do simplify, because I want this part to first get simplified, and then I want to do intros so that the simplified version goes up there. and then I do discriminate, and that solves it. Okay. Now let's move to another tactic, but before actually using the tactic, prove this theorem. This theorem is called F equal. And basically what it says is that if x and y are the same, and I apply the same function to both of them, I get the same value. So in other words, if x is equal to y, then f of x is also equal to f of y. And this holds for any type a and b, any function f that maps from a to b, and any elements x and y in type A. So in some sense, we are proving a polymorphic theorem now, because I'm saying this holds for every types A and B. So the proof is actually very easy. It's just a simple rewrite. Yeah. So I do intros. This is what I have. Oh, and by the way, it changed the names to x0 and y0 because apparently I have x and y somewhere else. So it decided to change the names. But anyway, my assumption is that x0 is equal to y0. I want to prove that f of x0 is equal to f of y0. But I can rewrite using my assumption. So I can say rewrite h. I can change the x0 here to y0 by rewrite. Okay. I could also do the rewrite in the other direction. I could change the y0 to x0. It doesn't really matter. And then I have the same thing on both sides, so I can say reflexivity. Okay. So as an example of this, again, I told you that constructors are also functions, right? So I can say that for any two natural numbers n and m, if n is equal to m, then the successor of n is equal to the successor of n, because s is also a function. Okay. And the proof can be that I can just repeat the same thing, or I can say I do intros and then I just apply that theorem, just apply f equal. Right. So if I say apply f equal, it understands. And look at this. So when I say apply f equal, in f equal on the right hand side, I have f of x equals f of y. And here I have s of n equals s of m. So Koch understands that it should replace f with s, x with n, and y with n. Okay. Now, when it does this, I have to also prove x equals y, because that's how apply works. So I have to basically prove that n is equal to m. But I have that as my assumption, so I just say assumption. Okay. So here's the thing. Instead of actually writing this theorem and always using it, since this is a very common theorem and we need it all the time, I don't have to actually say apply f equal. There is a tactic which is literally called f equal. And I can just use that. So if I want to show that s of n is equal to s of m, it's enough if I show that n is equal to m. So if I use the f equal tactic, it just tells me, okay, now prove that n is equal to. And of course, this is sufficient. So, and I have it in the assumption. So this is basically what I already wrote. Here's another example. Try this one. For all natural numbers a, b, c, d, if a is equal to c and b is equal to d, then the list ab is equal to the list cd. Okay, so let's say I do intros. And well, I don't like it that my hypothesis looks like that. So I can first destruct the hypothesis. So I can say destruct h so that I have a equals to c and b equals to d separately. But now what happens if I just apply f equal? Right, because these are lists, right? So again, I have to constantly do this. Set print all, printing all. I always forget what to write. Yeah. So these lists, they're basically created by the cons constructor. right? So if and I told you that constructors are basically functions. So if I do F equal, I will already get that I have to prove these two things. Now, why does it look like this? So on the left-hand side, I have cons of A and the list that only contains B, because remember, cons always added one element, head, to the beginning of a list, which was the tail. So that's why you get that the head here, which is A, should be equal to the head here, which is C. And also the tail here, which is not just B, it's a list that contains only B, should be equal to the tail here, which is the list that contains D. So that's why when I do F equal, it says prove these two things. Okay. Now the first one, this is an assumption, so that's good. Here I can do F equal again. Because again, this is cons of the element B with the empty list, nil. And this is cons of D, nil. Okay, let me again do this, set printing all. Yeah, the first one is cons of B nil. The second one is cons of D nil. Okay. So I do F equal again, and it says, well, it understands that nil is equal to nil. So it doesn't want me to prove that, but it asks me to prove that B is equal to D, and I have that as an assumption. And that's it, QT. Okay. But one thing that we saw here was that actually sometimes I don't want to just apply a tactic to my goal. I want to apply it to one of the assumptions or one of the hypotheses in my context. So for example, I did this here, right? So I had this, I had H, which said A equals to C and B equals to D, and I wrote destruct H. So this destruct was not applying to the goal, it was applied to the context. So let's see more examples of this. Let's say that I want to prove this theorem, which is basically the same thing that we've proven so many times. Oh no, actually it has a combination of equals, question mark, and equals. But it basically says that S is injective again. So I want to say that for every N and M, which are natural numbers, and every Boolean B, if Sn equals question mark Sm equals question mark always returns a Boolean. If this is equal to B, then N equals question mark M is also equal to B. So in other words, if next of N, if the successor of N is equal to the successor of M, then N is also equal to M. And if it's not equal, then this one is also not equal. Okay, because B can be both true or false. Okay, so I want to prove this. I first do intros. And what you see here is that I have this hypothesis H, and it's too complicated. So I want to simplify H. I don't want to simplify my goal. If I just write simple, I will simplify my goal. But I can say simple in H, and it will try to simplify H. So, and simplification just uses the definition of equals question mark and the definition of S. We've seen how simplification works before. So I say simple in H, and you see that it just gives me N equals question mark M. Because the definition of equals question mark was that if I have S of N and S of M, they're equal if and only if N is equal to M. So I do this. And then at this point, I just have my assumption. So I say assumption and QT. As you see, the proof was much simpler than you would expect. Okay, prove this one. Prove that for all N, if 0 equals question mark N is true, then N is 0. So basically, this one is a proposition, but this one is a Boolean. But we're saying that they kind of correspond. If the Boolean is true, then the proposition holds. Okay, so let's do intros first. Now, again, I have a case where I'm comparing N and 0, so I would like to do a casework on N. So I say destruct N, And again, as usual, n prime is just going to stand for n minus 1. So the first case is the case where n is 0. And in this case, I say, let's do intros again. I have to prove that 0 is equal to 0, reflexivity. My second case is when n is not 0, n is the successor of n prime. Okay? And again, I do intros. And remember last time that we were trying to prove this, this is where we got stuck. And then we had to go back and figure out that, oh, I cannot do intros here. I had to first do simplify and then do intros, right? But I'm going to do intros already here. And then I'm going to say simplify in H. Okay? And now in H, I have false equals true, and I can say discriminate H, and that's it. In the same sense, I can also use symmetry and apply and things like that in my context, in my hypothesis, instead of applying them on the goal. So here's another theorem. It says that for all n, p, and q that are natural numbers, if n equals m implies that p equals q, then m equals n implies that q is equal to p. Okay, again, it's a very trivial thing. So let's do a proof. We do intros. So these are all the things that I have. I want to show that p is equal to q. Now, ideally, I want to start from h0. Remember, before we used to do this backward reasoning, but now let's say that I want to really do forward reasoning. So remember, I told you that as humans, we think forwards usually. We start from the assumptions and we try to get to the goal. Whereas the normal way of thinking, the standard way of thinking in Koch is to do the opposite. Start from the goal and try to get back until you get the assumptions. But let's say I want to prove this as a human. I want to say m is equal to n, therefore p is equal to q. Okay? So I want to start with h0, and then I want to apply h and so on. Well, my first problem is that I have m equals to n here, but I have n equals to m here. The order is swapped. So I say do symmetry in h0. So remember what symmetry did. When we had an equality, it just swapped the two parts. But it did that in the goal. I'm now saying do it in h0. Okay. Now, the next step, and this is actually forward reasoning, whereas we used apply for backwards reasoning before, is that I say, now apply h in h0. What does that mean? That means that, well, h0 is the left-hand side of h. So if I have this implication h and I have h0, I should also have the right-hand side. I should have p equals q. But this is how I write it. I say apply h in h0. And of course, I can also give it a name. So I'm going to call it h1. I'm going to say apply h in h0 and call the result h1. So h1 is going to be p equals q. And as you see, I just got h1, which says p equals q. Now I can do symmetry, which turns my goal into p equals q, and then I can say this is h1. Or I could do symmetry in h1, and then say that this is just an assumption.